Join us. I'm going to start now. So this talk is about SMP on ARM, and it is about SMP in kernel space, because there you see the problems of SMP and memory coherency in general to a greater degree. They in principle also exist in user space, but that's a different field. Okay. So, a few basics first, so that definitions are clear. SMP has the basic characteristics that we have multiple CPUs, but they operate on the same memory, and they also share the rest of the hardware. So the main difference here is that you have, not main, but only difference here is that you have multiple CPUs. And in user space, you don't see this because your task as such runs on a single CPU and it runs as a single thread. You do not get, unless you use shared memory, access to the address space of other tasks. And even if you do that and need to coordinate with other tasks, you have special libraries. Main example, pthread, which does the job for you. In kernel space, this is not the case. The kernel always accesses all memory, the physical and the virtual address space of the task calling into kernel space. And so all CPUs operate on the same memory without any benefit of helper libraries. So, this may be boring. Well, no, it may not be boring. It is more boring, but it is necessary. Memory cells have addresses. As we are in an SMP system, those addresses are equal across all CPUs. And on ARM and x86 and most CPUs, but I think Alpha, you can address a single byte as the minimum. You can address more, but you need not. Those memory cells have values which remain unchanging, hopefully, or your memory is defect. And they do not depend on which CPU reads them. Which theoretically need not be the case, but no sane system does that. But this is the point for the static case, and therefore I'm going to make it now, so that there are no misunderstandings. Modern CPUs have a feature called the cache. Actually, usually several levels of them. It, as the name says, caches units of main memory read from the main memory, or values to be written into main memory. The cache itself cannot be addressed. In user space, you do not get to execute the special instructions usually needed to manage the cache. And one of the most salient features of caches is that they have a quite large granularity, much larger than the main memory. The typical value is about 128 bytes, going up all the time, because this granularity determines how much extra management memory you have to use for your cache. And those specialized memory management instructions operate on the cache line as their smallest unit. That is going to be important when we come to DMA. Now, I'm going to talk about memory ordering and cache coherency, which is a rather special case of memory ordering if you look at it from the right angle. There are three kinds of ordering I'm going to talk about. The first one is the ordering between different CPUs of the same system, between the CPU and secondary controllers in the system, and the CPU and DMA. Any questions so far? If you have any, feel free to ask. So, let us enter the fourth dimension. Our programs need to alter memory from time to time rather frequently, or they are useless. That can be done in several ways. Actually, in two. Either the CPU can access memory. It does so as its code directs, and to the code, any access happens exactly in the order that that code determines. The problem here is other CPUs typically don't execute the same code as the CPU your programming is running on, so they do not know that order. We shall come to the significance of that point a bit later. And let me before that, get to the second kind of memory access. It can be accessed by DMA. DMA, do I need to define it? Oh, let's do it for the general public. It's memory, we for our purposes here can define it as memory access for input and output by things other than a CPU. That means that you cannot use locking to synchronize access to memory areas used to for DMA. Locking requires your CPU to work. DMA controllers cannot do that. Locking is that what you use to ensure that changes to memory happen atomic. That is a special term here, means that a task that is not your task either sees the full result of your manipulation or nothing at all. If, in that case, any action is reduced to a simple action, memory ordering does not happen because you cannot order a single event. That is, if you do not use locking, then the events your code do acquire an internal order, and other CPUs may act differently depending on that order. So, let's look at that. So, this is not to say that locking is bad. Locking usually is a good thing. It simplifies code, and although it has an obvious cost, you need to take the lock and release it, that should not trick you into assuming that lockless coding is better. Yes, it does not have that obvious cost, but it has hidden costs and it is more complex. And I'm going to talk about some of the complexities here. Okay, let's go to a conventional example. You are inserting a new element into a singly linked list. Basic task. You might think so. Now, what do you need to do? First, you alter the next pointer of the new element, and then you alter the next pointer of the element after which your new element is supposed to be inserted. That is not new. That is also the case if on a UMP system you are writing lockless code and you get an interrupt between the first and the second step. If you were to reverse those steps and get the interrupt after your new first, formerly second step, the next pointer of the new element would be followed and nobody knows where, you crash. Difference arises on an SMP system because you have multiple CPUs, and we need to ask ourselves, what does the other CPU see while it actually simultaneously reads your list? And in asking those questions, we are using a thing called a memory model, which is drastically different between ARM and x86, and not just ARM and x86, but basically between everything and x86. Memory models concern themselves with the order of events. What happens after which? Dry matter, I know. So ordering of events on another CPU can be noticed by the CPU you are running on by the memory they alter. So you read memory and then you observe the contents. And obviously what you observe depends on the order in which you read memory. A change that has not yet happened by the time you read your memory cannot be seen by you, and vice versa. So that means that the ordering of events a CPU observes depends on the observer, and obviously it depends on the execution. If something technically and physically happens after something else, you will see it in that order, unless by mistake. So, how do we determine orders of events? We do so by the means of a memory barrier. A memory barrier is a special CPU instruction. To understand what it exactly does, we need to get a bit into the theory of the kernel. The kernel itself is written for a theoretical worst case, which is incidentally almost identical to the alpha architecture. The assumption of the kernel is that writes can happen in any order, and reads also can happen in any order. This is almost true for ARM. Writes can happen in any order. Reads, under some conditions, can happen in any order. Now, to understand why this is so, you need to ask yourself, what is your CPU supposed to do if it encounters a read instruction and can, for some reason, let's say TLB miss, not fulfill it? And I have two options. Either you wait, or you do something else. And in the course of doing something else, you will sooner or later encounter another instruction to read from main memory. And then you need to make your decision. Do I keep my instructions in order? Then I will now wait and stall, or I do not. And then the events may be reordered by reordering reads. The same also applies to writes, just to a lesser extent, because writes can be buffered. So, that is the model the kernel is written on, and it was introduced with alpha. The problem in the meantime is that alpha is dead, and most kernel development takes place on x86. x86 is a very nice architecture. It never reorders writes. It does reorder reads under some conditions, but under very few conditions. That is what I was referring to when I said that x86 is better than ARM. In that regard, it really is. It is really better than the rest of the world. It is so at cost in the CPU architecture, but as a programmer, you don't see that. It is, let me be respectful to ARM, worse in many other features, but we write code, not compilers, so we really don't care about an arcane instruction set or two little registers. For our purposes here, we are concerned with memory coherency and ordering, and there it is bad. This is nothing new, and our kernel is totally equipped to handle it, but there are rules which you need to follow if you want this to be handled, and ARM really requires you to follow those rules. So we now have, for the first time in many years, actually a test case for our multi-architecture support. So, the kernel implements three basic kinds of memory barriers. One which orders writes, one which orders reads, and one which orders everything. On ARM, these actually map to those three instructions. The processor takes a hint, so it can order more, but these three instructions for barriers in principle exist. In the kernel, they are supplemented by the SMP varieties. The SMP varieties are there because ordering between CPUs, of course, only matters if you have multiple CPUs. So, how are they used? This is, I believe, yes, to be the most, well, understandable example of a memory barrier use, which probably points to memory barriers not easy to use, and I would agree. It is from the FIFO code, which is written with the assumption that you can use it locklessly if you have one reader and one writer. And if those readers and writers actually operate simultaneously on different CPUs. So, this is the code for putting values into the FIFO. And the putting of values into a FIFO involves two steps. First, writing the value into main memory at the correct position. And then, not at then, but and, updating the pointer to the next value to be stored, or if you implement it the way that the pointer points at the current content of the FIFO, then you would, before that, increase the pointer. Anyway, the kernel model operates on the assumption that the pointer points to the next value to be written. This is a bit hard to understand because the FIFO code in the kernel is a bit optimized. It assumes that your FIFO is an order of 2 sized, so it is never necessary to actually wrap the pointers around, but the masking is always done. So this code is actually correct, but you need to look at it for an extended period of time to understand why. So you can see, first, we're doing the masking operation to determine the actual index. Then we put the value to be put into the FIFO into main memory. Then we do the memory barrier, and then we increase the pointer. On a single processor system, this code is obviously correct. On a multiprocessor system, it is correct only because we have the memory barrier here. The reader needs to know the index for new data for the simple purpose of comparing that with the index for read data to determine whether there is anything in the buffer. So, the buffer would become corrupted if those steps were to be reversed, because a reader would then read the already updated pointer, but not read the data written into memory. So this is the crucial order of the data here. I hope I made clear the relevance of the ordering of the operation here. Any questions so far? Let me point it out again, perhaps. Here, we have... I am too small for this. Here we have the masking operation, which computes the actual pointer because of the limited size of the FIFO. Then we have the write operation, the memory barrier, and then the increase of the pointer. And that is always necessary to have lockless operations on true SMP systems, as are practically every system today, to function correctly. The point here is that it would not fail on x86 under any circumstances without the write barrier. The corresponding read barrier is necessary on x86, but the write barrier is not. This was actually discovered with linked lists on PowerPC, therefore the example. Okay. Let's go to the next ordering constraint. There is an ordering issue with other accessors of memory which are not CPUs. Because this is so, we have SMP and non-SMP varieties of our barrier operations. Basically, they do the same thing, if they do the same thing, which, well, is tautological. So let's put it this way, they either do nothing or the same thing. Therefore, you can always use the non-SMP variety if you're unsure, but in case you're sure, please use the SMP variety. Well, they would be better on a UMP system, but basically who cares these days? Anyway, the kernel uses a conditional compilation and either makes them identical or reduces the UMP variety to a kernel barrier, to a compiler barrier, which does nothing more than tell the compiler that no, you must not reorder anything around this operation. So what the code says must actually be translated into machine code here. Now, why do we do this? In your typical laptop, you have well, not but several USB controllers, perhaps a Firewire controller with almost 100% certainty, an Ethernet controller, on very modern systems, perhaps a Thunderbolt controller, and of course you have the internal graphics. All those chips do access main memory, and not just in the manner of DMA, but to actually read their own instructions. Yes, we do have in the kernel primitives for reading into I/O space, but first of all, I/O space, not main memory, and modern controllers read their instruction from main memory, and they only work in respect with each other. So yes, if you write to PCI space, your writes do appear to everything in the system in that order. If you write something into memory, it does not need to appear so for any part of your chipset that is not a CPU. On ARM, on x86, again, that will work. So, no testing. Let's look in this a bit further. Your modern I/O chipset has perhaps something based on the ohci standard, Open Host Controller Interface. These are programmable to a surprisingly large degree. You more or less describe to the chip the I/O transfers you want to have done and not do them. So you write a program about this, a few transfers, and then you return to the already running program. You write this in main memory and put a jump to subroutine instruction in the already running program of your controller, where you, in wise view and consideration for the future, you left a few knob instructions, which can be replaced by jump to subroutines. So, here, the order of doing stuff is again important. First, you write your new code for the I/O controller, and then you place the call for the new code into the already running code. In your driver code, this is done by logic. You will write the new code and then the transfer call. But if you do not regard the memory ordering on writes correctly, it may happen that this new code, or only parts of it, will be written, and your I/O controller will read this and do very, very bad things. Crash, write to random parts of the main memory, call other parts of the main memory. It is simply not predictable. Usually the result of such an error would be a kernel panic, and one that is almost impossible to debug. So, let's look at the actual implementation. This is from USB code. That's the queuing function of the actual transfer descriptor here. At least its last part. You see, up to the memory barrier, your transfer descriptor is filled out and hashed, and then there is a memory barrier, and this here is the instruction for changing the execution pointer of the ohci controller. From the moment this instruction here hits main memory, the code is live and may be instructed. Execute, sorry. Again, here the order is extremely important. And here, because this applies to any hardware, however many CPUs it may have, we do have the right memory barrier in the not SMP variety. Okay. So, in the course of reviewing drivers over a long time, I've seen a lot of things that can go wrong. The first one is you have two events, the first of which is a read and the second of which is a write. And then some people are clever enough to put first in a write barrier and then say a read barrier. That is not equivalent. A write barrier orders writes and a read barrier orders reads. If you need to order a read and a write, you need to use the full MB instruction. And catching this, that was hard. The main case where this happens is that you give a command and then look, oh, what is my I/O controller doing? No, you must put a full MB there. Then I found, and frankly experienced it myself, that it is easier for the human mind to understand why you need to order writes, but it is hard to understand why you need to order reads. So people tend to put in the write memory barriers, but forget to put in the read memory barriers. Because this is so, and we come to the effect that in almost all cases, for each write memory barrier, there must be a corresponding read memory barrier, and vice versa. The kernel coding style insists that you put a comment to each memory barrier pointing to its equivalent. If there is one, in theory, it is possible that you have an ordering issue with multiple callers of the same function, but that is truly rare. There's one case or so in the kernel of this. What also tends to happen is that you have a mixing of I/O primitives and main memory accesses. That happens when your chip is a bit older and you do not put a jump to subroutine call in its limited machine code in the main memory, but you write a description of buffers to be written into main memory, and then you do an I/O access. Many a bit oldish SCSI and Ethernet controllers operate by that model. In that case, although the access to I/O space is perfectly ordered, it is not ordered with respect to the main memory access where you've written the description. There you need to put in a main member, a full member, a write memory barrier. Okay. Questions so far? No. Then we now come to the dreaded area of cache coherency and DMA. This is perhaps the hardest to understand point I'm coming to here, because in addition to memory ordering, it also involves the effect of caches, but it is the problem that most driver writers most readily encounter, and then get an angry email from me, please fix the DMA rule violation in your driver. I've written dozens of those, and I want to stop. Let's look into history. The issue is known for a long time, about 11 and a half years now, bordering on 12. As I said, the problem is not limited to ARM. It also happens and happened on PowerPC, and was actually discovered with the very humble source of a USB mouse. It produced weird results from time to time. And there was a guy named Roland Dreyer who really found the source of this, and we should admire him. This was a mean piece of debugging. So, why does this happen? DMA moves data between devices and memory. So far, so good. There is an obvious race. Do not touch the buffers while DMA is in progress, or you may read the old or the new content. That has nothing to do with caches or memory ordering. That's basic programming. But there arises an additional issue which is caused by caching. In the abstract world, your buffer is just an area of memory. It has an address and a length, and there you go. Because DMA does not have access to your MMU, that buffer also needs to be contiguous in physical memory. But, okay, the kernel memory is so. The only problem you would have is if you tried trying to do zero copy I/O, then you have the problem that data in user space is fragmented by the MMU. That does not concern us here. We're asking ourselves, what is the problem with caches? So, when a DMA controller does a DMA, the data has to hit main memory. Now there is a case. What if that memory is cached? Then there are two basic options. Either you change or throw away the cache. That's what x86 does. Or you do nothing. And that's the option that some models of ARM chose. It may be obvious that doing nothing is a dangerous option, but dangerous in which exact way? Now, let's consider two cases. Either you use DMA for output or for input. If you do it for output, and only main memory is looked at by the DMA controller, then what you have written into that DMA controller, into that buffer under program control, better be what is also in the main memory, and not stored for a limited amount of time in the cache, or you write garbage, more or less. For input, the problem is a bit harder to see. If you read from the buffer before your DMA is finished, you obviously read the old content. And that old content is outdated. that is a point where logic still applies. The problem is here that need not only happen when you read from the buffer, but it can happen if you read some other parts of memory. And that is a non-intuitive effect which needs a bit of explaining. As I told you before, the cache is organized in cache lines. Now we need to consider the scenario where a cache line holds your buffer and something else. So everything is all right. You don't read from the buffer, but you innocently read something else. The whole cache line gets transferred. There is something in your buffer, something old in your buffer, but it is now cached. And here comes the interrupt. DMA is finished. Fine, I'm going to read my data, read that buffer, get the old content. Now you're in trouble. There is nothing you can do by this point. You simply have to avoid it. And to avoid this problem, the kernel again abstracts it in the way that we have a DMA model. In the DMA model, there is a buffer, and that buffer is either fit for DMA or fit for CPU access. There is no gray area in between. There are primitives which transfer the buffer between those two states. Either you may do DMA or you may not do DMA. The primitive for mapping is map single, which means now you may do DMA, and if you unmap a bit, then no more DMA. There are a few elaborate helpers on this. You've got a scatter-gather variety, you got one for a whole page, and so on. Does not really concern us. When you are in the practical difficulty of writing a driver, you will very rarely use this. The USB layer in the generic part will do the mapping for you. If you're writing a device driver for some kind of USB gadget, you submit your data to the USB core, it maps. If you're writing for some reason, well, on ARM, maybe that's an actual example, a new host controller driver, USB core will handle you already mapped data. So knowledge of these operations is not what you desperately need if you do this. But you need to know about their limitations. So, their limitations are that you really must not touch the buffer. In particular, that means that your operations have to happen again in an exact order. First, you put the data into your buffer, then you map it, then you start your DMA, then you're sure that your DMA is over, and then you unmap it. Strictly speaking, mapping and unmapping need not correspond, but do it anyway. That verification of the end of DMA is a surprisingly hard point when you write a handler for timeout. You then need to make sure that really your DMA is not going to proceed, because whenever you're writing a handler for a timeout, you are racing against the hardware. There is the unlikely case that your I/O was exceptionally slow and really completes, although the timeout was already called. Furthermore, in theory, the mapping functions can fail. Then you need to use a bounce buffer. Fail due to limited address space or whatever. Then you really need to look at the ordering constraints here listed. In practice, how do we do this? We do not know the cache line size of our CPU. And we really must not. For us, we stay with the model of the logical buffer given by a starting point and a length. And the hardware does translate this abstraction into the appropriate invalidation or flushing operations on the cache line, and computes by itself and with the help of architecture-specific code which cache lines are to be flushed or invalidated. You are not supposed to concern yourself with that. For you, the only question is, where do I get clean buffers which do not share their cache lines with anything else? You do that by obeying those rules at any time and not to share a buffer for multiple purposes. There always happen those clever people which have 3 sources of DMA, 1 large and 2 small, and okay, we can be efficient here. Let's allocate 1 buffer large enough for the large transfer, and while that does not go on, we share the buffer between the 2 other operations. Does not work for this reason. And furthermore, if user space handles you a user space address for using data, do copy it in a special buffer. If you want to do 0 copy, yes, it would have more performance, but you have to make sure that user space does not touch that page in which its buffers, or in worst case pages, into which these buffers are put. And that's not as simple as it looks like. So, no sharing. And keep your cache lines clean. That's what it boils down to. The kernel knows the cache line size of the CPU or can determine it. You don't care. You just get a clean buffer, and you get it from kmalloc, and every kmalloc will give you something which is suitable for a buffer, and you use that memory allocation for 1 buffer and 1 buffer only, and for each buffer you use your own kmalloc, and you put nothing else in it, and don't share it. You may recycle it if you really want to, but that's what it boils down to. Okay, no sharing. We're strictly selfish here, and all is right. Good. Any questions? Our standard disclaimer. Yeah, was too theoretical a thing to talk about, but you get very subtle bugs there, which are extremely hard to debug, because obviously if you put any further instruction there, you mess up the whole timing, you will not see anything. Yes, I am supposed to hand you this microphone.
Have there been recently or whenever some bugs that have been in the kernel for a long time and then they were discovered when ARM was used? Because ARM SMP is not that old.
Actually, the one real bug we found was the one with the mouse. And this was fixed a long time ago. We routinely find such DMA bugs, but we find them by visual inspection of the code. We can, from the laws of great numbers, deduct that some of the random crashes that happen are caused by this. But there is no way to find this, because this depends on the timing in a very sensitive manner. If you put switch on dynamic debugging or something else, it won't show. Good, then we can end here and hand over to Josef.
Yeah, just we will